In this practical, we will be looking at the basics of how to analyze your data. We're going to look at some visualization techniques, drawing scatterplots and drawing boxplots, and we're going to look at the statistical techniques that fit with them. So that would be regression and correlations and analysis of variance. But we're going to start by just talking a little bit broadly about running analyses and the options that you have. Also, just to highlight how this falls within the analysis and interpretation of data. So this meets aim 1 and 2 for this practical, or the practicals for this module. Now, data analysis is key in all scientific techniques, so whether you're studying microbiology or genetics or plant ecology, you will find that there's a lot of the basics that are in common for all of these fields. Now, there might be different specialized methods, there might be different research focuses, but there's also a lot of common ground. So this can be hopefully a nice recap for everyone. Now, you can use any software you like really to run analyses. There are a lot of different packages available. All of them have pros and cons. But what I'd like to suggest is that you consider giving R a try. R is a rapidly developing statistical software package. It is written by anyone who wants to contribute to it. It's open source, so you can see exactly what's going on in every component of it, and it's also free. I've provided the links there to the R project and where you can download it. Its major downside is that it's a command line interface. That means you don't click and it does something for you. You have to type in what you want it to do. But even that isn't a big limitation, because there are packages that you can download again for free that will provide an interface that you can use a typical Windows approach of just clicking and getting your answers. Also, it's worth having a look at tryr.codeschool.com. It has a really very user-friendly tutorial to kind of get to introduce R and the basics. So yeah, give it some thought, give it a try if that interests you. For the assignments that we're going to be working on, you're going to be expected to analyze your data. You won't necessarily be expected to do statistics on your data, but that is only a benefit. Now, one can work in Excel. It's what I think a lot of us are most familiar with. The data analysis tool pack would need to be installed on your computer, and there's some links to show you how to do it. And that provides you with some basic statistical techniques. However, you really need to be careful, especially when you're doing this as part of a research project or when you're working on data professionally, about using Excel for your analyses. There are several computational bugs which have been documented, which means that sometimes Excel will just give you the wrong answers when doing analyses. It's also hard to make sure in Excel that you aren't making mistakes, and it's even harder to be able to repeat your analyses. And then again, there are links there highlighting some of the problems. So be aware of that. If you're most comfortable working in Excel and you don't want to push yourself and try to work in R a bit, then Excel is fine as an alternative for now. Okay, so for today, we really want to split our data questions into two types of analyses. So here we've got two columns. The first one asks, is there a relationship between altitude and species richness? And then there's two other questions. The second column, does species richness differ between north and south facing slopes? And two other questions. And I want you to tell me, how do these two groups of research questions differ? And maybe as a hint, this might help some of you. How would you visualize this data? So I'd like you to take a moment and pause here and think about how would you visualize this data, or if that doesn't help you, just how do these two groups of research questions differ? Now, the way that they differ is how their predictor and response variables can be characterized. So if we're asking a question, for example, of how does species richness differ between two slopes, we can see there that species richness is our response variable, because we're asking how it is affected, how it responds to slope. And that then makes slope our predictor. Slope is going to predict what the species richness is. Okay, so it's worth having that clear. We've got a response variable which depends on our predictor. We could say, for example, that on average the marks for a class depend on how much study effort is put in. We could say that the amount of plant growth as a response variable depends on the amount of fertilizer in a field. Okay, so let's think back to the previous slide. The column on the left, we asked, for example, how does species richness vary with soil moisture? Okay, and what we have there is we've got a continuous response. Species richness can be between 0 and, for example, 100 species. And our predictor, if it's soil moisture, is also continuous, because your soil moisture could be from 0% to over 100%. Again, when you've got this combination of a continuous predictor and a continuous response, then it's appropriate to use correlation and regression techniques. In contrast, if our predictor is categorical, in other words, it's not just a range of numbers, but instead it has discrete categories or classes, then we are going to use an analysis of variance, which is abbreviated to an ANOVA. So in our second column on the previous slide, we saw how does species richness, that's our continuous response variable, depend on aspect, which then is a categorical predictor, right? Because it can be north or south, or in our case, north or south or flat. There are other methods if we have a categorical response variable. So if our y variable, our response variable, for example, is the presence or absence of a certain plant species, then there's, two categories. It's present or it's absent. And if we have a continuous predictor and a categorical response, in other words, how does the presence of xerophyta depend on vegetation height, that would require logistic regression. And if it was a categorical predictor and a categorical response, so does the presence or absence of xerophyta depend on aspect, then a chi-squared or a g-squared analysis would be appropriate. Now we're going to focus on those first two types of analyses, but you're welcome to come talk to me if you're interested in the other two categories of analyses. So, we can visualize a continuous response and a continuous predictor using a scatterplot, and a categorical predictor and a continuous response variable with a boxplot. So this is where we're going to kind of... So, a scatterplot. This is what a scatterplot's going to look like if you draw it in Excel, just using all the defaults. There are at least 4 problems with this visualization of the data. So I'd encourage you to pause here and just think or try and identify those differences. Okay, so let's switch over to how the scatterplot should look. And you see that looks fairly different. First thing is that we've labeled our axes. So you see the x-axis is rock cover with the units, % shown in brackets, and species richness now a clear label on the y-axis, so we know what's happening here. We also have removed the heading And we've removed the little figure legend because neither were necessary. And we've also removed the horizontal guidelines. I don't know why Excel adds those, but in scientific publications you won't see those. Okay, so this is then how a scatter plot really should look. And more interestingly, more relevant is the interpretation of the scatter plot. So the basic message here is that the pattern of your points reveal the presence of relationships. So here we see species richness versus rock cover. And what would you say is the trend? As rock cover increases, do we see species richness get higher or lower? Now the way we would formally test this is by adding a regression line to the plot, and this is showing the trend in the data, and you see that it's a negative trend. As rock cover increases, species richness decreases. So here we have a visualization of a continuous response and a continuous predictor, and what we need next is then the statistics to show whether this is a relationship that could happen just by chance, or whether there is whether this is something that we are confident about. But before we get to the statistics, let's have a look at the difference between correlation and regression. Now, correlation just examines the relationship between two variables. It doesn't say this variable is more important than the other variable, or this variable affects the other variable. Whereas in regression, we examine the influence of one variable on another. So we assume causality. What that means is we assume that the change in one variable causes a change in another variable. Okay, so let's see if you understand this. For the following 4 analyses, which would be the most appropriate, correlation or regression, for these pairs of variables? So seed mass and distance. You can pause here if you want to think about it. But what we see is that this is better suited to a regression analysis. Why do I say that? Well, as we change seed mass, we can imagine that dispersal distance will change. However, if we move a bunch of seeds further from their parent plant, in other words, if we change dispersal distance, we're not going to change seed mass, right? So that is why there's causality here. Seed mass, we believe, is going to affect dispersal distance. What about species richness and endemism? Well, I would say this is an example of a correlation because there's no clear driver. Does species richness drive endemism? Does endemism drive or cause species richness? We don't know. A correlation is appropriate. What about range size and germination speed? What do you think? I would argue that it's a correlation again that's most suitable, because range size and germination speed don't necessarily directly affect each other. And a final example, flower longevity and pollination success. This would again be a regression, because the longer a flower survives, the greater its chance of pollination success would be. Therefore, there's a causality which we're assuming. So, in a correlation, we're examining the relationship between two variables. And the output from a correlation will be an R value. So what does this R value look like? It's a number between -1 and 1. And if it's positive, it suggests a positive relationship. So the same way that you have a positive relationship here, you see how as soil moisture increases, biomass increases. So there we have a positive relationship. If that was the inverse, in other words, if it was a negative number, there'd be a negative relationship. As one variable increases, the other decreases. Now, the magnitude of R, the closer it is to 0, the weaker a relationship. Okay, and the closer to 1, the tighter the relationship. So our two graphs on the right hand side, you can see this. An R value that's very close to 1, suggesting it's a positive relationship here. And because it's close to 1, because it's far from zero, it's a tight relationship. You see that as soil moisture increases, there's a clear increase in biomass. In the second panel, you see there's a lot more scatter in the data. There's still obviously a positive relationship, but there's a lot more scatter. It's a looser relationship. Now, regression, where we're examining the influence of one variable on another, we get several, well, in fact, we get 3 outputs. Okay, and here is a standard output from Excel. You get the same thing from R. And what we see is we first have a coefficient here, okay, a value that's getting multiplied by our predictor variable, our X variable. Now, just with a correlation, if the slope is positive, it suggests a positive relationship. Here, we see that as rock cover increases, species richness tends to decline. So it's a negative relationship. That's why it's minus 0.1. And the steepness, the magnitude of that number represents the steepness of the relationship. So here, for every 1% rock cover increase, there's a minus 0.1 change in species richness on average. If that value was minus 1, then it would mean for every 1% increase in rock cover, we'd lose 1 species. So that would be steeper. Yes. The intercept is this number over here, and that represents what the value of y will be when x is 0. Okay, that's sometimes useful. In this case, it suggests that when rock cover is 0, we'll have on average 12.4 species. The third thing to look at is your R squared value. Now that in a way is a bit like your R value from correlation, and in fact they're mathematically linked. It's also called the coefficient of determination. It ranges from 0 to 1. And what it does is it explains the proportion of variation in your response variable that is explained by your predictor. So in other words, here we see that 12% of the variation in species richness is explained by rock cover. So that's not a very high proportion of variation to explain. Now, the slope and the intercept are what you need to draw this regression line, and that's important for us because it allows us to draw this best fit line or this regression line to see what the actual pattern is. Okay, so just to give you another example, there's the first example of species richness versus rock cover, and a second example of species richness versus bare soil. The second example, when we fit our regression line, that's what we see. You also see that our R squared value is lower. So bare soil is not a particularly good predictor of species richness. Indeed, rock cover is a better predictor. You see we have a weaker slope also, so the relationship is less strong. Now, correlation and regression analyses also give p-values. Maybe you remember this from your biometry course in first year. It is a topic that we could go into a lot of detail, but we're choosing to be very brief with it here. I'd encourage you to go dig out your first year biometry textbook and have a read. But essentially what we're saying is that this p-value is a probability. Okay, that's why it's got the p. Probability that the observed pattern reflects random results, random patterns. Okay, in other words, the chance that the pattern that you see is not true. So it's the chance that your data, that there's no relationship between the two variables in this case. In other words, the p-value here is the probability that there's no pattern between species richness and rock cover, or the probability that there's no relationship between species richness and bare soil. Now, there's a threshold that is generally accepted of 0.5, in other words 5%, and that's the threshold before we call a pattern significant. Okay, and that's the likelihood that the pattern that you're observing is not just due to chance, that there really is a relationship between species richness and rock cover, as an example. Okay, so I'm going to give you a quick cheat sheet for correlations and regressions in R. In Excel, you would just go to the Analysis toolpack and click Regression, and you can kind of follow the steps there. In R, one of the biggest difficulties is just importing data. And if you can provide your data as a text file, so you can save it in that format in Excel, you can then read it in by just saying read delim, open brackets, file.choose, close brackets, close brackets. And then your data will be imported into that data1 object. Okay, and then you're able to plot your data. This is just saying look in the data1 object and take column X, and you'll then need to put in whichever your predictor column is there and your response column is there, and then here you can type what the name of your X and Y axis should be. You can do the same for a correlation, the same for a regression, where you add, using this AB line, you can add the best fit line. So if you're interested in giving R a try, this is one of the things you could do. Okay, so let's leave Scatterplots behind and let's think about a box plot. Now, as we've said already, it shows a relationship between categorical predictor and a continuous response variable, and it asks the question of, is there a difference between groups? Now, those who are doing experiments, and you guys have all got your seed germination experiment as example, this will be a really important way to visualize that data. Okay, so let me ask you, how would we visualize such data? Let's stick with our idea that you guys are going to be examining for the short report. Is there a difference in species richness between the north and south aspect? Any ideas how you would visualize that? Well, if you were to take your data from in Excel and tell Excel to just plot it, this is what you'll get, and you can well see that there's something strange here. How can you have an aspect that ranges from 10 to 60? That doesn't make any sense when our raw data is north versus south. And indeed, this is where Excel does something rather stupid, and it just plots 12, 15, 10, 15. You see 12, 10, 12, 15, 10, 15, 15. Right? It's just plotting the numbers in sequence. We can fix this by converting the n's to 1s and the s's to 2s. So now 1 represents north and 2 represents south. And we can then also clean that up, give it proper labels, so that looks a bit better, north and south. And there we visualize the data. Now, these symbols might be overlapping a lot, so it's difficult to tell what's really happening there. And that is why we will sometimes use a box plot. So we can convert this column of data into a box. See the box there, and whiskers, that's your whisker plot. So what does this mean? Well, let's just look at half of it. We see that box and whiskers plot gives us a measure of centrality. What does that mean? It means it shows us a typical representative value. And here, that's represented by that line. So this in particular here is showing us the median or middle value of the data set. It also tells us two measures of variability. Now, the box here is representing the interquartile range. Okay, that's maybe a confusing name, but essentially it's saying 50% of your observations lie between here and here. So our typical or representative species richness on the northern aspect here is about 9 species. And 50% of your observations lie between 6 and 12 species richness. Okay. And finally, the whiskers tell us the range. So we see at lowest there were 2 species in a plot, and at maximum there were 18. Let's go back to the north and the south data. What do we see? Well, would you say that the median values here are very different? Would you say that the variability of the data is very different between north and south aspect? And I think the basic answer here would be no. We wouldn't say it's very different, and therefore we wouldn't say there is a real difference between the north and south aspect in terms of species richness. Okay, but let's look at an example where we do see a bit more evidence. This is again data from the Galliesburg from a previous year, and we look at species richness as our response versus topography as our predictor. Here we have the three topographic categories, and there you see a difference in the median values. Not a big difference, but there is still a difference. Let's then take an extreme example, and this is made up data. But you see we've got two panels there on the right. The first, we have species richness of about 20 species for the north and 40 for the south. And you see the same for the second panel. However, in the second panel, there's a lot more variability in the data. Okay, so we see that the medians are the same for the two plots. But then think about this. In which plot is the difference between the two aspects clearest? And why would you say so? Well, I think most people will agree that the difference is clearest in panel A. And why is that? Well, we see that the difference between north and south is bigger than their variability, right? Here in panel B, you see that the variability of the data is very high. And in fact, the variability here is bigger than the difference between north and south. Okay? So in other words, what we can do is we can look at the ratio of variation between groups to variation within groups. Okay, so variation between groups here is the difference between north and south, and the variation within groups is this for the north and here for the south. Okay. And this, indeed, this ratio of variation between groups to within groups is what is used to calculate the F statistic. Now, here you can see a large F statistic in panel A and a small one in panel B. And this is just telling us that there's a lot of difference between the groups here relative to the difference within the groups. And when that number is high, we've got a lot more confident that there's a real difference. Okay, so the p-value here is going to reflect that, and that's just the probability that the difference is due to chance. Okay, so if we have a small p-value, which is going to be the case here in panel A, it's going to say there's very little chance, very little probability that this is just due to chance. In other words, we are pretty confident that species richness really does differ between the north and the south, even though we didn't sample the entire north slope and the entire south slope. Okay, now this F statistic and p-value form the basis for the analysis of variance. Okay, so a quick cheat sheet for box plots in Excel. There's a really good tutorial on dummies.com. There's not really an easy way to draw them, but look at the data analysis toolpack and that'll help you through. In R, it's much easier to do this. You just use the boxplot function, and you'll see again, you tell it that, for example, your data is stored in the data1 object and in column Y. So the red there you need to replace with what your columns are called, and you give it an appropriate label for the X and Y axes. And that summary, open brackets LM, well, that'll run in ANOVA for you. So it's quite nice and simple to do.